how do these devices interact with the outside world? So we're digging into the actual hardware of the device now. There's several different common concepts that are implemented by most of these devices. Starting off with general purpose input-output. These are simply pins on the chips that either go high or go low. They're either on or they're off. And that state can actually, affect other things on the board or even things outside of the device. So for example, oftentimes if you want to turn on a light, let's say it's a lamp plugged into a wall, you want to turn that lamp on. You're not going to switch the alternating current through the device. What you're going to do is you're going to pull a GPIO high, which is going to trigger a relay, most likely a mechanical relay, that's going to close a switch and turn the lamp on, as an example. Two protocols, or rather four protocols, that are commonly used in IoT devices. We have I2C, or I2C, stands for Inter-Integrated Circuit. And we have Serial Peripheral Interface, or SPI, followed by UART and USB. Now, I have a whole bunch of acronyms here on the slide, so let's go ahead and run through these. For I2C, by the way, I2C it's pronounced many different ways. You might hear I2C, I2C, I squared, IIC, a whole bunch of different options. I prefer I2C, so I'm going to keep saying that. We have SDA and SCL, that's serial data and serial clock. I have a picture of what an I2C implementation will look like here in just a moment. For SPI, all three of these are the same. It's just different acronyms to describe the same functionality. And the reason we have a change, particularly right here, is a change in terminology, entering the world today. So serial clock, serial data in, serial data out, and chip select. Followed by serial clock, controller out, peripheral in, controller in, peripheral out, chip select. And then finally serial clock, and then the original terms that were deployed whenever these I'm talking 1970s stuff here. We had master out, slave in, master in, slave out, and then slave select. So these terms have been replaced with either COPI, SIPO, or SDI, SDO. And so if you see an older data sheet referencing SPI and using MISO and MOSI, that's what it stands for. Master out, slave in, slave out. Those terms have now been replaced primarily with SDI, SDO. However, and I'm going to go off on a little tangent here, this leads to ambiguity. It's the same ambiguity that you see when you're talking about UARTs. So UARTs, Universal Asynchronous Receiver Transmitter, they have two signals that are absolutely required, transmit data and receive data, and then maybe some flow control like CTS, RTS type stuff. So here's the ambiguity that I'm talking about. Whenever you have two chips, and you want to talk UART, transmit is from what perspective? It's usually from the chip that you're talking about. So transmit of this device must go to the receive of the other device. It's the same problem with this SDI, SDO. So SDI is now specific to the chip, whereas with SPI and using controller out, peripheral in. So SPI is a bus. You have the controller device, controller out, and peripheral in. It's always the same direction. There is no ambiguity there. It's leaving the controller and it's being received by a peripheral. With SDI, serial data input. Now we're talking about, is it input to the controller or the peripheral? Who knows? Sorry about the little tangent, but this particular terminology here leads to ambiguity that is very similar to the ambiguity that we have in UARTs. This problem's been around for 50 years. The perspective when talking about the transmit signal. Next up, we got USB. So you do see USB a lot in IoT devices. Plug it into your computer or plug it in simply for power. Just to power the device, plug it in with USB. This is what I2C looks like. So we have positive voltage, negative, ground, serial clock, serial data, and then pull-up resistors to bring these signals up to positive voltage at any given point. We have a microcontroller. I2C is a bus. So you'll notice this looks a lot like an Ethernet bus. You have peripherals and a microcontroller. Microcontroller will run the clock, or the peripheral will run the clock. It depends on who's talking, and then clock data out on the serial data pin in blue. Here's that picture I drew uglily a few minutes ago. So we have a microcontroller and a peripheral. The transmit signals are with respect to the device that is in question. So transmit of one must go to receive of the other. What protocols are we going to use for connectivity? How do we talk to the network? And the network here is not necessarily IP. The device has to connect to a network in order to get data out. It could be talking to a gateway, or it could be talking directly to the internet. What protocol are these devices going to use? There's a whole bunch of them out there. You'll notice that we have Wi-Fi and Halo. Both of these are wireless standards, 802.11. Halo is relatively new. It's 802.11ah, and it's like 1 kilometer, low power, battery powered Wi-Fi. Cool stuff. We have Bluetooth. Bluetooth is not IP, so you're going to need some form of Bluetooth to IP gateway. We have cellular protocols over here. LTE category M1 and narrowband IoT. Sigfox is a proprietary cellular protocol. We got LoRa for low power, long range stuff. Zigbee, built on 802.15.4, so there's a whole bunch of protocols that can be used. Zigbee is commonly used in mesh networks. And 6LoWPAN. 6LoWPAN is awesome. It's 6LoWPAN is IPv6, low power, personal area network. Pretty sure that's what it is. But the point here being that it's IPv6 built on top of 802.15.4, which is the same underlying protocol that Zigbee is using to give you mesh networking. It's cool stuff. But you're going to need a 6-to-4 gateway or be able to talk native 64. You will need the gateway from 802.15.4 up to IP. It gets pretty complicated. How do we talk at the application layer? So this is that picture where I had device, gateway, internet. Regardless of if the gateway is there, the data's got to get up to the internet somehow. There's a whole bunch of protocols that can do that. If the device is talking IP directly, then you could implement this protocol on the device itself. MQTT is one of the most common application protocols for transport of data from a sensor. I read the temperature value, I got to get it up to someone to ingest. MQTT is message queue telemetry transport. We have CoAP. This one is also extremely common. It is constrained application protocol. Advanced message queue protocol, message queuing protocol. Very simple control protocol, lightweight machine to machine. HTTP REST. You could just simply do an HTTP post from the device, provided it has that IP connectivity, or the gateway receives the data over whatever that backend protocol is and sends it up to the HTTP server. And then, if you want to get crazy, you can make your own, and then you won't be able to interoperate with anybody. MQTT, like I said, it is one of the most common protocols used for taking data from IoT devices and getting it up into the cloud. Stands for Message Queue Telemetry Transport, created in 1999 by a group called Oasis Open. Oasis Open also created AMQP. There are encryption and authentication options available for MQTT, however, they're not required. And time to market will often dictate whether or not it's actually implemented. Keep that in mind. If you are analyzing an IoT device and it's talking MQTT, is it encrypted and authenticated? Here in the picture, we have an example of MQTT in operation. We have a device that has a temperature sensor. Right here, there may or may not be a gateway. That gateway's job would be to connect the device's network to the internet. So let's just assume, for the sake of this picture, this particular device has IP and has some form of MQTT client built into it. So this device would connect to an MQTT broker. The broker's job is it's a matchmaking service. It connects publishers to subscribers. Anybody can be a publisher, anybody can be a subscriber. In this case, the client is publishing to a topic. That topic is called temperature. And then we have subscribers to that topic. We have a cell phone here that is subscribing to the temperature topic, and this MQTT backend system is also subscribing. So as this sensor publishes its data, it's being ingested and stored. As well, we have real-time notifications going to a cell phone here. So pub, sub, publish, and subscribe protocol. Next up, we have Constrained Application Protocol, or COAP. It's very much like RESTful HTTP, and its intent is to be used on low-power, lossy networks. It is defined in an RFC, published in 2014, and as we can see here in this screenshot, we have a request-response code, and you'll notice that the verbs listed here in these methods are very similar to what you see in HTTP. So you're publishing a state that is accessible via something that looks kind of like RESTful HTTP. Gateways. The job of these gateways is to bridge from one network to another, if they're even required. The device could do IP, may or may not need a gateway. So for example, Bluetooth Low Energy to TCP IP. You could use an IoT gateway for that. Another example, 802.15.4 with 6 low pan, you need to get that data to IPv4, you're going to need an 802.15.4 gateway. These gateways can also pre-process, correlate, package data prior to getting it up to the internet. As well, they could store data locally in the event the internet connection goes down, and then publish it when it comes back up. Finally, up in the cloud, where, up in the internet, this data needs to be received, it needs to be stored somewhere, we need to monitor state, as well as configuration of devices. There is this concept called a shadow, which is a replica of the device up in the cloud. So you could query the shadow, and that's the last known state, regardless of whether the device is online. Device comes online, publishes its state, and then the shadow is updated. Also, over-the-air updates are very common. Device comes online, it sees it's running an old version, it can download the new firmware. Provisioning usually also handled by some form of internet-based system for registration of the device or distribution of certificates. Some of the higher-end IoT devices can run containers, often referred to as fog computing. This might be a Cisco term, but it is, as they say, it's like the cloud but closer to the ground. So you're taking the compute and pushing it out to your edge devices so that they can have some local intelligence.